We're working through the 10.2, 10.5 worksheet number 1. Find the surface area generated by revolving the curve about the given axis. So we have a parametric equation here revolving around the x-axis. And so the formula for surface area revolving around the x-axis is 2 pi integral y times the square root of x prime squared plus y prime squared. So we just follow the formula, x prime, y prime. We can find the derivatives. 2t becomes 2. 4 minus 2t becomes 2 as well. And we plug into our formula under the square root, and then replace our y value back in terms with t. So y gets replaced with 4 minus 2t. We can work this through a little bit more here. 4 minus 2t times this becomes root 8. Root 8 gets pulled out as a coefficient, and then we can go through a power rule for the integrand, and then plug in upper and lower bounds, and we're going to get our way down to 8 pi times root 8. Okay. Number 7, we're going to find points of horizontal vertical tangency for r is equal to 1 minus sine theta. So if we sketch the graph of 1 minus sine theta, this is what this looks like. If we want to figure out horizontal tangent, then that's when dy over d theta is equal to 0. So so theta being the independent variable, and we want to find the rate of change of y with respect to theta being 0. That will produce horizontal tangent lines. So we can convert our equation to in terms of y. So we know that y is equal to r sine theta, and then r is 1 minus sine theta, so we're just going through the work here. Distribute through, we get sine theta minus sine squared theta, and we can now find the derivative of y with respect to the independent variable theta. So sine theta becomes cosine theta. Sine squared theta, we're going through chain rule here, so bring down the 2, keep the sine theta, and then subtract 1 from the exponent, so 2 becomes 1, and then multiply by the inside function's derivative, which is cosine theta. Now this is double angle formula that we can expand to be, well, actually, I'm sorry, we're factoring out the cosine theta. So factor out the cosine theta, we're left with 1 minus 2 sine theta. We can set both portions equal to 0. So cosine is equal to 0 at 3 pi over 2, and 1 minus 2 sine theta is equal to 0. Solving for sine theta, first off, we get 1/2, so theta is equal to pi over 6 and 5 pi over 6. All right, and pi over 2 is also a potential horizontal tangent, but eventually we're going to see that because this is going to conflict with the vertical tangent, that this will have to be removed, but we can come back to this. All right, potential vertical tangent, we can set, we know that x equals r cosine theta. Replace r with 1 minus sine theta, so we can distribute through, so cosine theta minus sine theta cosine theta. And here we can find the derivative. Cosine becomes negative sine. Here we can go through product rule, so f prime g plus fg prime. And if we clean this up slightly a bit more here, cosine squared and sine squared, and then we can try to convert everything to be in terms of just one trig function. So it looks like it'd be easiest to convert cosine squared to be in terms of sine theta, so we have everything in terms of sine. So cosine squared gets replaced with 1 minus sine squared theta. Combine like terms here, we get 2 sine squared minus sine theta minus 1 equals 0. Go through our factoring procedure here. 2 sine theta plus 1 times sine theta minus 1. We get sine theta equals negative 1/2. Sine theta equals 1. Sine is equal to negative 1/2 at 7 pi over 6 and 11 pi over 6, third and fourth quadrant. And then sine theta is equal to 1 at pi over 2. We know that horizontal and vertical tangents can only occur if either the numerator is 0 or dx d theta is 0. But if there's a conflict, meaning that they both, if it's an angle that makes both dy d theta and dx d theta 0, then we have to eliminate that as neither a vertical nor a horizontal tangent. Okay. All right, so we want to find we want to find the points in polar form here. So here we have theta is 3 pi over 2. So if we want to find horizontal tangent, we can plug these theta back into r, and then to get it into a form of r comma theta. Okay, theta is our independent variable, but the way that's presented is going to come as the second value here. All right, so if we plug 3 pi over 2 in for r, we get 1 minus sine of 3 pi over 2, which is equal to 2. Pi over 6 gives us 1/2. 5 pi over 6 gives us 1/2. And then 7 pi over 6, plug this in for theta, and we get 1 minus sine of 7 pi over 6, which gives us 3/2. And then same with 11 pi over 6, we get 3/2 as well. Okay, back page. Number 8, find the area of the region inside the circle. R is equal to 3 cosine theta, and outside this dimple limicon 2 minus cosine theta. So 3 cosine theta, we have a graph that looks like this here, and then R is equal to 2 minus cosine theta, dimple limicon here. You can use our calculator as well to sketch the graph. All right, we're trying to figure out the area of the region that is inside the circle. So inside the circle, but at the same time outside the dimple limicon. So it's going to be basically this portion here. Okay, so this portion and this portion. However, I'm just going to focus on finding this area here, because if I find this area, then I can double it because of symmetry, and then go from there to find the total area. But I'm just going to focus my attention on in this first quadrant here. All right, so we know that area is created, polar area is created through these wedges, these pizza wedges, sliced pizza wedges that kind of comes from the origin, and rather than rectangles as in rectangular graphs. So first thing we need to do is we need to find intersection, right? Let's figure out how far we need to rotate around to find the area. So we can set the circle equal to the limicon here to figure out where their intersection is. So if we set 3 cosine theta is equal to 2 minus cosine theta, solve for cosine theta, we get cosine theta equals 1/2, so theta is equal to pi over 3. So we know that we're going to be concerned about the area from 0 all the way to rotate it all the way to pi over 3. All right, so if we find the area that extending from the origin all the way out to the circle here, then that will give us this entire region, including the space that we don't want. But we're going to start off with that. We're going to start off with, and the formula is 1/2 integral r squared d theta. So the radius that we're going to create first is just going to go directly out to the circle here. So 3 cosine of theta squared, and we're going from 0 to pi over 3. So that will take care of all the area between actually in this entire circle here, okay, or in this entire half circle here. So that takes care of the semicircle. But we want to subtract out the portion that we don't want, because we only want the area that's inside the circle, but then also outside this limicon here. So we're going to figure out what the area is of this region. So from the origin, we're going to create another area that we're going to subtract out, and that will extend from the origin to the borders of the dimple limicon between 0 and pi over 3. So 1/2 0 to pi over 3 r squared. My radius now is 2 minus cosine squared d theta. So now this whole expression will give me the area of just this portion in the first quadrant. All right, and then if I multiply this area by 2, then I'm going to be able to get to the total area that I need, which is the portion that is in the first and the fourth quadrant here. So if we work this out using your calculator, come out down to be 3 root 3, or equivalent to roughly 5.196.